Okay, so what we're looking at here is triangle ABC, and specifically we're concerned with H, which is, whoops. Okay, H is the orthocenter of the triangle ABC. That is, that it's the intersection of the altitudes, the perpendicular drop from B to AC, from C to AB, and from A to BC. So first we need to verify that the orthocenter actually exists because, well, normally in most cases 3 lines would have 3 points of intersection. So to do this, let's start by making some parallel lines. I'm going to draw the line that goes through A and is parallel to BC firstly. It's not very parallel, but it'll do okay. And then I'm going to draw the line which is through B and parallel to AC. And finally, I'm going to draw the line through C, which is parallel to AB. Okay, as you can see, these don't quite join up. I'll just fix that up here. Something like that. Okay, not a very good triangle, but that's okay. So I'm going to label this triangle here. I'm going to label it as triangle, that could be F, that could be E, and down here the bottom vertex is going to be D. And what you might observe, since these lines are parallel, is that triangle ABC is the medial triangle of triangle DEF. That is to say that B, A, and C are the midpoints of FD, EF, and ED, respectively, right? So that is to say that these triangles, ABC is similar to DEF, and ABF is similar to DEF as well, and we've got 5 similar triangles going on here. But we're only really concerned with firstly verifying that this is in fact the medial triangle, and to do that we'll draw some parallelograms. So the first parallelogram, I'm going to draw it here in yellow, is parallelogram EABC, right? And you can see that because it's a parallelogram, we define the sides to be in fact parallel. You can see that EA is going to be equal to BC because opposite sides in a parallelogram are equal. Secondly, we can look at our second parallelogram, which we'll find in this pink color, and it goes from AF BC. Okay, and you can see that parallelogram AFBC actually has the same base as parallelogram EABC. They had the same base, and if they had the same base, the other sides are the same. So clearly EA, and let me write this, the line segment EA is congruent to the line segment AF. And we can similarly conclude that for the other sides, that FB is the same as BD and EC is the same as CD, right? So this is clearly our medial triangle. And what do we know about the medial triangle? Well, let's investigate because we have parallel lines here. We can look at some angles in parallel lines, and if we have that the angle down here, I'll call this HA. Angle AHAB is right, then we also know that angle HAAE, and I'll draw this angle here. This angle here is also going to be right. They're both going to be right angles because we have angles in parallel lines. Okay, so now if these two lines are equal, then we can say that AHA, that the altitude from A in the triangle ABC is the perpendicular bisector of EF, since A is the midpoint of EF. And we can do the same thing for the other 3 altitudes. We can say that these 3 altitudes are actually the perpendicular bisectors of the triangle DEF, right? So what do we know about the intersection of the perpendicular bisectors? Well, since the perpendicular bisector of a length is equidistant from two points, the endpoints of the segment, we know that the point, the orthocenter H that we've marked, is going to be equidistant from E, F, and D. And it's the center of the unique circle, which is defined by E, F, and D, right? And we know for a fact that that is, in fact, the circumcenter. H is the circumcenter of EFD. And since a triangle only has one circumcenter, because the circle is defined uniquely by 3 points, we conclude that the altitudes, which are the perpendicular bisectors, must in fact intersect. So the orthocenter of ABC does in fact exist because it is the circumcenter of EFD. Okay, so now we're looking at a triangle again, and now we're going to be talking about the Orthic triangle. So the Orthic triangle is the triangle which is defined by the feet of the three altitudes in a bigger triangle. So you can see there's the Orthic triangle right there. Right? And the Orthic triangle has lots of properties, but the main thing which I want to identify right now is that we've made a whole bunch of cyclic quadrilaterals, and maybe you can't see any circles yet, but we have a whole bunch of cyclic quadrilaterals here, right? So I'm going to outline 6 cyclic quadrilaterals that are made in any triangle where we do this kind of thing. So let me get a pen here. We'll start with the light blue, some aqua. So the first cyclic quadrilaterals we have are these ones. Okay, so you can see this quadrilateral, and why is it cyclic? Well, it's cyclic because we have a 90-degree angle here. This angle here is 90 degrees. And also this angle here is 90 degrees. And we know that if opposite angles sum to 180 degrees, then the quadrilateral must be cyclic. So necessarily, all of these other ones also are going to sum to 180 degrees. And what we also know about this is that the diameter of this circle, which is made by this cyclic quadrilateral, is going to be CH. Because you can see from the converse of Thales' theorem that because CH is subtending a right angle, the arc subtended is 90 degrees, clearly it is the diameter of the circle, right? Okay, so now let's see. We have a few more cyclic quadrilaterals which look exactly the same, right? So we get these diagonal ones in here, and you could of course see that the AH is going to be similarly the diameter of this circle, and finally BH is the diameter of this final cyclic quadrilateral. So you can see we have 3 cyclic quadrilaterals, sorry, in triangle ABC. So now let's turn our attention to really the same triangle XYZ, and I'm just using a new triangle so we can see properly. Right, we're going to find some more cyclic quadrilaterals. So first we look at the feet of the altitudes, and once again we have to draw in now. Sorry, I'll draw a little better line than that. Draw in our Orthic triangle. Right, and given our Orthic triangle is like this, we can find our cyclic quadrilaterals in here. Okay, so we link the midpoints of the two sides. So one of the sides of the Orthic triangle, and then come down to 2 of the vertices like this, right? That triangle is definitely going to be, it's definitely going to be cyclic. How do we know this? Well, we know this because we have this angle right here is a right angle, and this angle right here is a right angle, and both of these angles are kind of subtended by xy, right? And so we have these 2 angles, and they're equal, and they're both subtended by the same arc, and that implies that it's a cyclic quadrilateral, as we know, right? So now let's move on to what other cyclic quadrilaterals we can find. We can find another 2, okay? So if we pick these 2, and I'll choose a new color now because this diagram's a little more convoluted. We'll pick these 2. Right? You can see exactly the same thing once again. Okay, and finally, we can pick the two that we haven't used yet, which is these two, and we get another cyclic quadrilateral right here. Okay. Also, we can see where the diameter is going to be in each of these cyclic quadrilaterals. If we look at the aqua one again, if we have another look at the aqua one, we can see that the diameter is going to be the one that subtends the right angle. And so that diameter is going to be YZ, sorry. And the midpoint of the side of the triangle is going to be the center of the circle. Okay, so this time I've only drawn in two of the altitudes, but we can of course still find the orthocenter at H. So we have the altitude CF and BE, and we're going to do some angle chasing, right? We're going to do some angle chasing in here using the fact that this angle here, here, and this angle here are both right angles, right? And to do that, we can see, we have triangle CEB, right? We know that the angle sum of a triangle is 180 degrees, and we have a 90-degree angle in here. So this angle here is going to be, I'm going to write C and then a little right angle to be 90 minus C, okay? Or let me write that a lot smaller, actually. There we go. Okay, and also if we have a look at this angle here in the context of triangle CFB, right? What is this angle going to be? Well, it's going to be 90 minus B. It's going to be the complement of the angle B. Okay, so what about this angle on the other side? Right? We can see this in a couple of ways. Firstly, we know of course that the angles the angle in a line, in a straight line, is 180 degrees, so that's a 90-degree angle as well at BA. So in triangle BA, we know that this angle down here is going to be the complement of A. And likewise this angle is going to be the complement of A. I don't think I need to explain that now. Okay, so what we can see here, and we could also verify that those angles are the complement of A in another way, because if we have a look up the top, I'll write this down for us. We know that 90 minus B plus 90 minus A, right? So what is this going to be equal to? Well, it's going to be 180 minus B minus A, right? And 180 minus B minus A, if we look at triangle ABC, we know that that is going to be C, right? So if we look at over here, is really where I'm talking about, right? We could clearly confirm that angle, and we can do the same thing for the others. And likewise, if now I go ahead and I draw in the third altitude, it doesn't really look like an altitude, I'm not going to lie about that, but it is. This is a right angle. Okay, if I draw in this, we can see that this angle here is going to be 90 minus B, the complement of B. And this angle here is going to be the complement of C. Okay, so we have lots of angles in here already. Okay, so now I'm going to redraw our orthic triangle. Awesome. Now, if we look at the angles actually inside of the orthic triangle, to understand what these angles are going to be, we can look at some cyclic quadrilaterals. So I'm gonna highlight one of our cyclic quadrilaterals just to make an example of this. This one in particular. Right? So cyclic quadrilateral EH, this D down here. Let me quickly label D. Point D, right? So EHDC is cyclic, as we showed before, and looking at EHDC, we can see some angles that are inside of this. And the angle that I actually want to look at in particular is, okay, what is the arc, what length, what segment of along EHDC, what chord is going to subtend the angle, which is the complement of A that we found down here? What's going to subtend this angle? Well, it's going to be EH, right? And EH also subtends the arc, this arc here, which I'm highlighting, which is HDE. So these are going to be the same. The two angles in pink are going to be the same, right? Okay, that's pretty interesting. Because now if we look at what arc is going to be subtending the angle which is the complement of B, right down here, let me pick purple. Okay, it's going to be the angle HD. The chord HD in the circle, which is the circumcircle of that cyclic quadrilateral. And similarly, we can see that this is going to be this angle, right? So the two purple angles are equal. Now, if we highlight another cyclic quadrilateral in yellow, like this one, what is that? It's FBDH, cyclic quadrilateral FBDH. We can see that the other angle, the complement of C in the angle which is inside the angle B, which I'll highlight in maybe gray. Okay, it's subtended by the arc HD, the chord HD, and HD also is subtending this angle. And if I pick another color and we look at the complement of A, we can see that another angle which is the complement of A, we find it subtended by the arc FH, so it's going to be this, right? But wait a second, we said that this angle here is equal to the complement of A, and this angle here is equal to the complement of A, right? So this line DH through the orthocenter and over to A, that line is actually the angle bisector of angle EDF. And as I've shown, we could have done the same thing with the final cyclic quadrilateral, right? And if we do the same thing, we'll find that, in fact, these two angles here are both equal to the complement of B. And if these angles are both the complement of B, well, what do we know about that? Well, if they're both the complement of B, then we can also say that these two angles are going to both be the complement of C, right? So the point H in the triangle, in the orthic triangle, EFD, is the intersection of the angle bisectors in that triangle, right? That's quite impressive, actually. These are the angle bisectors. And also we can pretty clearly see that if that, say, like, I'm looking at angle AEH, that whole angle is 90 degrees, and we found the complement of B in there. So likewise, we also actually have the angle B here, and this is the angle C. And you can see with each of these little triangles on the side of the orthic triangle, they have the angles ABC in them, right? So they're similar to triangle ABC. So we have three similar triangles, and we also have that the orthocenter is the intersection of the angle bisectors, and that means that it's the incenter. It's the orthocenter of ABC is the incenter of EFD, right? So we have some triangle centers which are in fact coinciding. Finally, I want to identify like a pretty cool invariant which is in this triangle, and I want to show that as we move A along the circumcircle of ABC, so you can imagine that here is some of the arc. As long as we move A along that arc, we want to show that the length EF is not going to change. That's one of the sides of the orthic triangle. We want to show that it's going to stay the same. And to do this, let me turn my attention to the similarity which we showed before. We showed that this angle here is equal to angle B, and this angle here is equal to angle C, and we want to show, what we did show in fact, was that triangle AEF is, as it so happens, similar to triangle ABC. Okay, why is this important? Well, because we have the ratio of the two sides, EF over BC, and because when we do this translation of the point A, BC is definitely not going to change. So if this ratio is constant, then clearly we know that we're done. We're done because EF is not changing if this ratio is constant. And from our similarity, we know that as it happens, this is equal to AF over, and what's the corresponding side? Well, the corresponding side is going to be AC. Right? And what triangle contains both AF and AC as side lengths? Well, I want to turn our attention to triangle AFC. And triangle AFC is super important because if we can show that triangle AFC, as we move A around, all these different triangles with all these different values of A, you can imagine like the A1 and A2 along this arc. Triangle AFC is similar to triangle A1FC is similar to triangle A2FC. Well, clearly, in that case, the ratio of AF over AC is constant, and then the ratio of EF over BC is constant, and then we would be done. And let's show that. To show that, let's have a look here. How can we do that? Well, we have some important angles that are going to stay the same because we're moving along the circumcircle, and we have the chord BC in the circumcircle of ABC. This angle here is going to stay the same, right? As we move it around, because it's the same chord. It's being subtended by the same chord. Okay, that's really good, right? That angle is going to stay the same. And what other angle is going to stay the same? Well, the complement of A is going to stay the same. If A is conserved, the complement of A is also conserved, right? And we have angle-angle similarity. So all these triangles are going to be equal. Since this is a right triangle, we even know that the third angle. We even already know the third angle.